I'd like to welcome you to Polar Coordinates Section 9.5. Much like parametrics that we took a look at last chapter, I suspect that this is our first experience for many of you with polar coordinates. So a polar coordinate would be if we had a grid laid out where this is rectangular, and rectangular is our typical XY chart, and we said there was a building we wanted to get to that was down 5 blocks to the east and 3 blocks to the north, then we could travel to it down here and up there. But if it was nothing but open field in between here, we may choose to travel to it through the field to shorten our distance, of course. And I might use the phrase as the crow flies. We would say the distance from here to here, if we have to go by blocks, would be 5 and 3, 8 blocks, but the distance as a crow flies would be, let's see, this is 5 by 3, 25 and 9. This would be square root of 34, shorter distance. So polar coordinates are kind of like that. In fact, they're exactly like that. They take the whole city blocks out and just let us go directly to where we are. They give us an angle that we rotate, and then a radius, and I like to equate it to just kind of sitting on a swivel chair at 0, 0, getting to spin around on it. Same angle, like it's from the x-axis as when we worked in trigonometry. Same angle, and then sitting in that chair, we're going to throw a rock. So this would be, we're going to spin pi over 2, or 90 degrees clockwise, and we're going to aim that direction and throw the rock forward 2. So from here we spin pi on 2, spin around to here. We're facing this way, we're aiming this way, and we throw the rock 2 from there. And of course we lie on A. And here we rotate 3/2 pi, 1/2, 2/2, 3/2 pi. We're now aiming this direction on our chair, and we throw the rock 2, landing on D. And here we don't spin at all, and we just drop the rock. So it lands on C. It's definitely worth noting that this could be 2/3 pi or 0 2/3 pi, where we spin 2/3 pi, aim out this way, and we just drop the rock. It would be the same point. It would still be 0, 0 because we didn't throw the rock at all. And I bet you can figure out how we'll interpret this negative here. We're going to spin 5/4 pi, 1/4, 2/4, 3/4, 4/4, 5/4. We're sitting on our chair facing this way, but I throw the rock 2 backwards to B. So the plotting of these things, not so bad. Now there's some other things we're going to come back and talk to, this polar to rectangular and rectangular to polar, and I think I'm going to be able to convince you we already know these formulas. But let's go through some more of these examples on page 1. In 9 through 18, plot the given in polar coordinates and find 3 additional polar representations where we can spin a full revolution backwards up to a full revolution forward. So I'm going to plot this. I think I'll plot it right in here. So we spin, and I always read these from right to left. In fact, you saw back here, you might have noticed I wrote this from right to left because I always think about sitting on my chair and spinning and then throwing a rock. So we rotate 3/4 pi, we're aiming this way, and we throw the rock a distance of 2. And now we're supposed to find other ways that we could get there, and I'm going to start with our backwards rotations right here. I could rotate backwards this far in my chair and still be facing in the same direction. So that would be negative 1, 2, 3, 4, 5/4 pi. I rotated, and then I'm facing this way, so I once again just have to throw the rock 2. Okay, so there's 2 positive, or excuse me, there's a negative representation. There's 2 positive throws. Our other option is to get positioned aiming this way and throw the rock backwards 2. One way I could do that would be just to rotate this far. That's negative pi on 4. And the other way I could do it is to rotate all the way around to here 1, 2, 3, 4, 5, 6, 7/4 pi. Aiming this direction, but I need to land the rock back here, throw it over my shoulder, 2. Probably be a really good time for you to pause the video and try this problem. Nothing special about that square root of 2 whatsoever. Okay, number 16. If you paused and tried it, it would help you. We're going to aim 2/3 pi, 1/3, 2/3 pi. And we're going to throw the rock a distance of, whoop, hang on, we're aiming this way. Almost had to start this video over, but we're throwing backwards, so we're back this way, 5 square root of 2. That's the distance we threw the rock to here, although we were aimed that way. Okay, so there's a forward rotation I can get there. Would be all of this, 1/3, 2/3, 3/3, 4/3, 5/3 pi. That aims me in the right direction. I'm aiming this way, and I just throw that 5 square root of 2. Another forward rotation, I could just spin to here. Well, we've got that forward rotation already, so let's go with, I've got 2 forward rotations. Let's go with negative rotations. I could just spin backwards, negative pi on 3, and that gets me lined up with where the rock should land. Throw it 2. Or, of course, I could spin all the way back to here, negative 1/3, 2/3, 3/3, 4/3, getting me lined up in the opposite direction where I want to throw the rock. Throw the rock negative 5 square root of 2. Okay, and then we've got some problems where we're going to plot a point that's given in polar and then change it to rectangular, much like we could change this point up here. Let's say this was rectangular. This is more like number 36 and 40, but this point right here, 3, 5, should be able to be changed into that angle, square root of 34, and that angle. Okay? So let's plot this. This is given again in polars. Pretty easy to surmise that this is polars, 26 is polars, but we're at about 22. This means we rotate 0, so we're aimed out this direction, and we just throw 2. We just get to there. Rectangularly, that's also coincidentally the point 2, 0. But of course that won't happen very often. Okay, here we go. 5/2 pi. 1, 2, 3, 4, 5/2 pi. We're aiming this direction, but we throw backwards 16, so we end up, the rock ends up right here at negative 16. So that is the ordered pair 0, negative 16. And we'll find they're easier, quadrantal angles are pretty easy to handle in this format, or this type of problem. All right, we're going to rotate 5/4 pi. 1, 2, 2, 3, 4, 5. We're rotating 5/4 pi, aiming this way, but just dropping the rock. So another really easy one, rectangularly, where does it land? At 0, 0. And best problem on this section. We're going to rotate negative 30 degrees, or pi on 6. We're aiming out this way, but we're throwing backwards that way. This distance is 3. So we need to come up with, well, that was terrible. We need to come up with this x value, this y value. And normally, we know this is a 30, and normally in a 30, 60, 90, we might prefer to work with 1, 2s, and square root of 3s on a triangle faced this way. I understand that's a negative 3 if it was on here. So 2 is to 1 as 3 is to what? Well, 2 is to 1, I have to divide by 2, so y is 3 on 2. 3 divided by 2, and 1 is to square root of 3 as y is to x, or 1 is to square root of 3 as this is, as this y, 3/2, is to x. We have to multiply by square root of 3. 3 square root of 3 on 2. And that is a backwards, and y is an up. Let's double check those negatives all the time. Okay, and now the reverse. We have rectangulars, -3, -3, and we're supposed to find two sets of polar coordinates, but we're only allowed to go forward rotations here. So we could rotate with the most obvious one, and this is a 45, so 1/4, 2/4, 3/4, 4/4, 5/4 pi, and then throw the rock. Well, if this is a distance of 3 and this is a distance of 3, 45, that makes this a distance of 3 square root of 2. Throw the rock 3 square root of 2. I'm not allowed for this problem to rotate backwards. Again, theta has to be, our rotation has to be between 0 and 2 pi. But I could just rotate to here, aim exactly the wrong direction, pi on 4, and throw the rock over my shoulder, so -3 square root of 2. So, with the exception of perhaps, in fact, even 0, 0, any point out there, we can name it 0, 0, 0 being the exception. We can name 0, 0, rectangular 0, 0. We can name it any rotation 0. But any other point out there, there's always two ways that we can name it rotating forward a revolution, and two ways we can name it rotating backwards a revolution. Let's take a look here. 1, 2, 3, -1, giving me a 3 by 1, or -1 if you prefer. 3, 9, and 1, 10. We're throwing the rock square root of 10. Forward revolutions, I could rotate all the way around. Is that a 30-degree angle? I had a lot of people in class just assume that that was a 30-degree angle, but 30 degrees aren't in ratio 1 to 3 to square root of 10. They're in ratio 1 to 2 to square root of 3. So it would be nice to figure out, I'm not even going to call this theta here. I'm going to call this one, this angle right in here, I'm going to call it fish. It'd be nice to figure out what angle fish is. How can we figure out what angle fish is? It's not 30, it's not 45. There are other angles. This is an angle that produces a y on x ratio. Y on x is in ratio 1 to 3, or y on r is 1 to square root of 10, or x on r is 2 to square root of 10. But that means, see, here's what we know. We know that tangent of theta equals 1 on 3, or -1 on 3. But I'm only going for this acute angle. I don't care about it being the fact that it's a negative rotation. You'll see what we do with that. So how do we solve that for theta? Well, of course, theta equals tangent inverse of 1/3. And now we got to do some thinking. So how are we going to name this rotation that comes almost all the way around, except it doesn't, fish. It doesn't go fish. So how do we name that? Well, it's 2 pi minus angle fish. So we could rotate 2 pi minus tangent inverse of 1/3, and then throw the rock square root of 10. Or I could rotate right over to here, aim exactly the wrong way, and throw the rock backwards square root of 10. What would this angle, now this angle would of course still be fish in here. What would this angle be? Well, it's pi minus angle fish. So it's pi minus tangent inverse 1/3. Okay, or pi, just pi away from there. Okay, now some things that I'm going to claim we already know. I referred to it as our 2 a.m. wake-up calls because I should be able to sneak in your room at 2 a.m. in the morning, as creepy as that sounds, and say, what is the cosine ratio? And you should say, cosine of theta is x on r. And if I multiply both sides by r, I get r cosine of theta equals x. And sine of theta is y on r, so if I multiply by r, I get r sine of theta equals y. And of course, tangent of theta equals y on x, and r squared is in a Pythagorean relation as a hypotenuse with x squared and y squared. So I'm going to claim we know those. Well, how is this good? If I want to go from polar to rectangular, or rectangular to polar, if I've got an x in rectangular, I can turn that into r cosine in polar. Or if I've got an r times cosine in polar, I can turn that into x in rectangular. See, polars, we want things in r's and thetas, while rectangulars, we want things in x's and y's, and of course vice versa. So let's take a look and see how that applies. Some of these are really pretty quick and simple. In fact, I would suggest if you really understand what's going on, we could do 48 almost instantly. I think you'll see that, but I'm not going to do it as I really understand. Here we've got x squared plus y squared. In fact, it's still going to be quick. X squared plus y squared, and hopefully we would identify that and just turn that into r squared. And hopefully we'd just say, well, that's r squared equals 16. But what if we didn't do that? What if we said, okay, I got an x here. What do I know about x? Let's see. Cosine of theta includes x. So x is cosine theta times r. So this could be r cosine theta squared plus, how about sine? Sine of theta equals y on r. So y equals, multiply by r sine of theta. So this is r sine of theta squared equals 16. And this is a long way to go to get to a pretty simple problem. Square these, I get r squared cosine squared of theta plus r squared sine squared of theta equals 16. Now, ideally, and this is worth writing down somewhere, ideally, we tend to like to solve polar equations for r. And most times, rectangular equations we like to solve for y and put it in function form, but we're not always going to deal with functions. We're going to get circles and ellipses and sideways parabolas, so we'll talk about that as well. So if I'm going to solve this for r, I think I'm going to factor out an r squared, and I get cosine squared of theta plus sine squared of theta equals 16. And I would certainly hope we all recognize that. And then maybe realize, oh yeah, x squared plus y squared is just r squared. R squared times 1 equals 16. Now, algebraically, we would say r equals plus or minus 4. Square root of 16. But if you think about this, what this means is we can spin around and circle all we want. We can be aimed anywhere on here, and I can either throw it 4 this way or 4 back that way, or 4 this way or 4 back that way, or 4 this way or 4 back that way, etc. So we really can just name this r equals 4. Because r equals 4 gets us to all the points on here if I rotate all the way around. I could leave it this way and then say something like 0 is less than or equal to theta is less than pi, and I could get it done in just half of a revolution by taking 2 rocks with me. Aim this way, throw 1 forward, 1 backwards, 1 forward, 1 backwards, etc. So the other thing that I think we should note is, geez, this is just a circle with radius 4. Center 0, 0. Perfect. And we can get there. Okay, kind of a weird one. And just for the sake of it, I'm going to just treat this as x equals, and I know they say a is less than 0. They're just saying a is not 0 for some other problems in here. It won't make any difference for us in this. Let's just say this is x equals 5 for right now, just to take some of the mystery out of this. Well, what can we do with this? X, I'll just redo this. X is located in cosine, and until we get comfortable with this, you might want to just keep doing this. There's x, so what is x equal to? R cosine of theta. So we get r cosine of theta, now I'm in polar, equals 5, r equals 5 on cosine of theta, or maybe you would prefer that as r equals 5 times secant of theta, cosine's reciprocal. Now, if we stop and think about that, it's a pretty simple problem. But if we stop and think about that, kind of bizarre. Here's x equals 5. X equals 5 lies over here. Straight line. Okay, no big deal. Well, then let's take a look at this. So you're telling me we're going to get a straight vertical line, not working with x, but saying that the radius, the distance I throw the rock, and yet we understand cosine is just a graph that just goes up and down and up and down and up and down, and somehow or another we're going to end up with the same as x equals 5, and that just seems a little bizarre to me. So here we go. I'm going to go into mode and go into polar, and when I go into, let's go window, I think I'm just going to go x min 0 to 2 pi. Nothing magical about that, but x min 0, x max, let's go down, 2 pi, and stepping point 1, that seems good. When I graph this thing, it doesn't like it. I must have done something wrong in there. Let's go back into window, 0 to 1.1.1, negative 100 to 100. I'm just going to go negative 10 to 10, but I'm not sure that's where my error is. Let's go back to y equals, oh, I don't have an equation in here yet, of course. So I'm going to go r equals 5 divided by cosine of, and when I hit the X button, I actually get theta. They expect thetas in these polars. Kind of makes sense. And we go ahead and graph that. And sure enough, there's our line. Appears to be x equals 5. If I go to, let's see what happens if I go to trace. Puts me on it, and it says, hey, wherever I go on it, I'm actually tracing right and left now because it's changing our angle measure. X equals 5. Okay. All right. 58, this one is a load compared to the other problems in here. 64 is tough, but not like 58. Okay, I've got a y squared. If I had an x squared with it, like I could get a plus x squared with it, I could change that into r squared, as we did up here. But I don't, so let's see. Sine of theta contains y. So y may be replaced with sine theta times r. So this is r sine of theta squared minus 8. Likewise, I'm going to get r cosine of theta for x, and I'm going to go equals 16. Add 16 to the other side. I'm going to square this. R squared sine squared of theta minus 8r cosine of theta. Actually, I'm going to bring that 16 back. You'll catch on to what's going on here. And my first thought is, hey, I got things squared, things not squared, and no things at all here other than just a coefficient. So is this quadratic? No, because we shift from sines to cosines. It's quadratic on r squared, but then we have to deal with the sines and cosines. So here's where I would ask, what's better than having an equation with sines and cosines? And hopefully we would say having either an equation with sines or an equation with just cosines. Sine squared, as we should know if we're in this section, we can change to 1 minus cosine squared of theta, since sine squared plus cosine squared is 1. Minus 8r cosine theta, minus 16, which I've been juggling around. I guess I'll distribute here. R squared minus r squared cosine squared of theta minus 8r cosine of theta minus 16 equals 0. And at first look, I've got 4 terms, and I don't know what I'm going to do with those 4 terms, but if I ignore that first term, I've got r squared cosine squared, negative 1 of those. I've got 8 plain old r cosines. So I've got r cosine, all of it squared, a plain old r cosine, and no r cosines. This is actually quadratic on r cosine. I'm going to go r squared equals, add these minuses to the other side, plus 8r cosine theta plus 16. So what I'm curious about is, can I factor this into r cosine theta and r cosine theta? Well, are there factors of 16 that add up to 8? Yes, 4 and 4. It's actually squared. Oh, and this is an r squared. And there's our big payoff. I can take the square root of both sides, and I get r equals r cosine theta plus 4, and you may be saying, hey, plus or minus, but for much the same reason that we don't need plus or minus here, we can get away without it down here as well. So I've got r equals r cosine theta plus 4. Ideally, remember, ideally we solve for r, so I'm going to group my r's, factor out an r, factored it out. Let's see, what do I have here? I've got something wrong here. Grouped them, that's an equal to sign, sorry. Equals 4, and r equals 4 on 1 minus cosine of theta. And here's the question I asked in class that stumped a lot of people, and some people were rewarded for this. I said, well, what does the graph of this look like? I said, I want you guys to tell me what it is. And almost everybody grabbed their graphing calculator. Oh, no, we don't need a graphing calculator to know that. Well, maybe we could pick some values for theta and create a giant t-chart of this. But the graph of this is going to, in polar, looks just like the graph of this in rectangular. Don't let that be lost on you. And the graph of this, since this is a y squared, and if I added 8x to the other side would be a positive 8x, the graph of this somewhere, and I don't know where it is, but I know how it opens. It's a y squared parabola. The p-value is positive. We could solve this for y squared and figure out what that parabola is, but the graph of this thing, it's definitely a parabola that opens to the left. Okay. We might do something like this. We might here say, okay, you can look back up above, x is r cosine theta, so this could be r squared cosine squared, equals y is r sine of theta, so this could be r squared, r cubed, sine cubed. We can divide both sides by r squared, and I have an r sine cubed of theta. I can solve for r. It was cosine squared. Now it's on sine cubed, and that's pretty good. But can we simplify that if we think of this as cosine squared theta on sine squared theta times another 1 on sine theta? Cosine on sine is cotangent, and 1 on sine is cosecant theta, and I would say that is best solution. Okay, and now we're going to do things backwards. Oh, by the way, this final answer over here on number 52, I should probably now go back in and say that's r equals a secant of theta. I wanted to do the 5 just so we could take a look at the graph. Okay. So convert the polar equation to rectangular form. So now I want to go from thetas and r's, or r's and thetas. I want to convert that into x's and y's. That's our goal here. So r, if I have an r squared, I can make it x squared plus y squared. And a lot of people might be tempted to start by squaring both sides. But the first thing I would do is our 2 a.m. wake-up calls. I'm going to change that. So I'm going to get r equals 2 times x on r. And so what's the payoff there? Well, I've at least gotten an x involved, but I still have this r involved. But I could multiply both sides by r and get r squared equals 2x. And that is x squared plus y squared, r squared, equals 2x, which is great. Now we might want to solve this for y, but I would hope at this stage we recognize this is not a function. To solve for y, I'd have to introduce a plus or minus. This is a conic section. I've got a positive x squared, a positive y squared. They have the same coefficient. This thing, if the graph exists, this thing's a circle. So I'm going to try to set it up as a circle. X squared plus 2x, leave a blank, plus y squared equals 0 for right now. Half of 2, 1. Squared is plus 1, but that wasn't there. So I need to add 1 to the other side to balance it. I get x plus 1 squared plus y squared equals 1. Wow, that speaks to me. I mean, we're not asked for this, but that's a circle with center -1, 0, and radius 1. Okay, there's a circle with center -1, 0, and radius 1. Okay. Now, this is a problem. I relate this back to when you're going through learning equations of lines and you're given a slope and a y-intercept, and that's an easy one. And then you're given 2 points, and you're given a point and the equation of a line and that it's parallel to. And there's all sorts of different ways. And we get really good at finding equations and getting them down like y equals 3/4 x minus 2 into that form. And we're great at graphing these things too. We're great at graphing these. We know right where to start. But how are we at graphing this? Y equals 3. I can tell you I've been doing this a long time, and I've seen awfully good students graph that either this way or that way. And I think the thinking behind it is, well, y equals, y goes up and down, so it must be this. But I would read this as the height is always 3. My point being, we get good at the hard stuff that has both variables involved, and then we're not so good when we only get a single variable. Same thing here. What does this mean in terms of my rock and my chair spinning? This means I'm going to spin 11/6 pi, but I can throw the rock any distance I want facing 11/6 pi. I'm going to draw this. 11/6 pi gets us to right here. That's a 30. That's a pi on 6. I don't think I drew that quite to scale. So I would be spinning around this far, aiming this direction, but don't forget, I could throw the rock this direction, or I could throw it backwards. So we just need the equation of that line. And if this is a 30, 60, 90, for convenience, I could call this length 1, this length 2, this length square root of 3. This is negative because it's down. So what is our y-intercept of our line? B is 0. What's our slope? Our slope is to get from this point to this point, for instance, we go down 1 over square root of 3. Rationalize. We get our equation of our line is just y equals negative square root of 3 on 3x. All right, that's not so bad. Okay. 74, kind of an interesting one. This one very few people recalled from first semester. Sine of 2 theta. I can't turn that into y on r unless I do some kind of weird u substitution. But I can turn this side into x squared plus y squared. That's nice. And I can turn this into double angle identity. This is 2 times sine of theta cosine of theta. And that escapes some people. You'll see that quite a bit in calculus. You'll be expected to know double angles, double angle formulas for trig functions. So let's see. This is x squared plus y squared. I like that. We're going to x's and y's here, so that's good. So this is 2 sine 2 a.m. wake-up call is y on r. Cosine 2 a.m. wake-up call is x on r. So I get x squared plus y squared equals 2yx on r squared. But this is x squared plus y squared. I'm going to multiply that across. X squared plus y squared times another x squared plus y squared. This is our r squared equals 2yx. And I think the back of the book has this as just 2yx equals x squared plus y squared squared. You can try as you might. I don't believe you're going to improve from there. And a really good opportunity for you to pause the video and try. I would just tell you, I would not square both sides first, maybe later. But the first thing I would do is 2 a.m. this sign. And it's please pause video and try that. Welcome back. I'll bet most of you didn't leave, but I'll bet a few did, and you'll be all the stronger for it. R equals 2 on 1 plus y over r. at which point I think I'm going to cross multiply these fractions. R times 1 plus y on r equals 2. A little bit of a payoff here. R plus y equals 2 when I distribute. Solve for r, and I get 2 minus y. And this is really nice, except I can't have r's in here. Now I'm going to square both sides. And I get x squared plus y squared. Look ahead. Does it look like maybe there's a payoff for foiling that out? When I FOIL this out, I'm going to get a positive y squared. 4 minus 4y plus y squared. The y squareds cancel. I get x squared plus y squared equals 4 minus 4y. And at this time, I believe we have another circle. Or wait a minute. No, we don't. The y squareds cancel. Sorry. At this time, I believe we have a parabola. And you could probably leave it like this. I'm going to solve for y. You'll see why. I'm going to add 4y to both sides. I'm going to subtract x squared. It joins a plus 4. I'm going to divide everything by 4. So I get negative 1/4 x squared plus 1. And I would know immediately what the graph of that looks like. If you took this course, if you played parabolic charades, you know that this graph is up 1. It's opening down, and it's only 1/4 as tall. What usually goes over 1, up 1, over 2, up 4. What usually goes over 2, up 4 won't go over 2, up 4 anymore. It's only 1/4 as tall and upside down. Graph of this thing looks like this. I don't know if I could have. I don't know if I would have known that by looking at that. Okay, that's the assignment. Of course, you're going to have an assignment sheet with this. Good luck. Let me know what I can help you with.